Hi folks, this is exciting. It's our first real and truly first unambiguously calculus topic, and that's looking at amounts and rates of change. So jumping into that, we describe the amount of change of something as the final amount minus the initial amount. And this makes sense when you think about just in general, like how much older or how much has your age changed. You subtract your final age, your current age, from whatever age you were looking at earlier, your initial age. Or if we want to talk about how much money a business earned or lost, we take their current amount of money, their final money, and subtract how much they started with. Symbolically, we represent this as delta x equals x minus x naught, or x0. So this right here, that's the Greek letter delta. And so like I said, we say this as delta x equals x minus x naught, or x0. The x naught is kind of a more British or European way of phrasing it that came from a lot of my professors in university, so that's my habit, but x0 is perfectly acceptable. We're just expressing kind of the first x value. That's why it's got a subscript of 0. So when we look at a rate of change, we talked about how much something changes, but if we want to talk about the rate, we need to compare that change to another change. So we're always comparing changes to each other. So that's why it says always with respect to. So you can't talk about a rate without saying with respect to or implying with respect to. Sometimes instead of with respect to, you'll see the word per. So here's some examples. Position with respect to time. F of x with respect to x. Wealth with respect to time. So a lot of times when we're looking at stuff in the real world, it'll be with respect to time. If we're looking at graphs, it'll a lot of times be with respect to that horizontal axis, whatever that is. Those are just the conventions. But what we're saying is, how much does the position change compared to how much the time changes? How much does f of x change compared to how much x changes? How much did wealth change compared to how much time changed? And so that's what we have with these rates of change. We're looking at how much one thing compares to how much another thing changes. So to calculate that, the average rate of change is simply the ratio of the changes. So you can see up here, there's 3 versions here. We have version 1, which is delta f of x divided by delta x. We have version 2 right here, which is f of x minus f of x naught over x minus x naught. And then we have version 3 here, which is f of x plus delta x minus f of x over delta x. So what do we have? Why do we have these 3 versions, and kind of what's the point of all of those? Well, they're all looking at the change in the function on top. So change in the function on top over the change in x on the bottom. And it's just 3 ways of expressing it. So we can just do it kind of big picture, just say change over change for this left-hand one. We can write that out, kind of expand that by doing final minus initial over final minus initial on the second one. Or we can use this kind of fancy form that doesn't necessarily make sense right now, but it will make sense in a little bit. And that's by saying x plus some, amount of change in x. So basically you're saying, take my x value and then go over by a little bit by delta x. And that's going to give me my final x value over here. And so plug that into your function to get some point. And then just plug in the original point over here, and then we can see where we get those results. So we have this being f of x plus delta x. This width right here is delta x. And this right here would be our f of x. So we're basically looking at the change in y is just going to be the right-hand value here minus the left-hand, and the change in x is just that delta x. And so this is also called the difference quotient. And that's just the fancy big calculus word for this is the difference quotient. So next, what we'll look at is how do we find the instantaneous rate of change? Well, if we have an average rate of change based on some interval, if we just shrink that interval down closer, smaller, and smaller, that average is going to be better and better, right? Like if you can imagine a graph like this, if I compare this point to this end point, the average, it's pretty close. But if I compare this point to this point, then we can see that I align more closely. If I come in even closer to, sorry, that's not how we should draw this. Let me restart that completely. So if we erase all this, so imagine we've got a simpler curve. And we'll restart this. Imagine you've got a simple curve like this. If we wanted to find the average rate of change, if we wanted to find the rate of change at this point right here, where I've drawn this x, well, we can pick 2 points that are far away and estimate the average rate of change. And you can see that kind of matches up with, how much this x curve is changing. But if we come in closer, say these 2 points, you see that this much more closely aligns with the curve. So in other words, the closer we get in, the better and better our average gets. And that's exactly what we do for instantaneous rate of change. One way of expressing it is to say the limit as your little tiny change in x approaches 0. Well, that means that basically you're going to get closer and closer to this f of x point right here. Because you're going to start with, say, f of x, start with delta x as 1, then you make it 0.5, then 0.01, then 0.001, then 0.0001, and you see that you get this tiny change in the function divided by a tiny change in the x, which is effectively just zooming in really close to this point right here. The other way you can express that is kind of more directly of just f of a minus f of x over a minus x, where this is a mistake. This should be as x approaches a. Because then you're seeing that you have a tiny change in the f of x divided by a tiny change in the x direction. So both of them are looking at zooming in closer and closer and closer to a given point. It's just whether you express that as starting at your point and then moving a tiny bit, or moving your point, your initial point, closer to your starting point. The reason that we have both of these versions is basically that if you're wanting to talk about the function in general, the top definition is more useful. If you're wanting to talk about a specific point on the function, the bottom expression is more useful. And when we get to the practice problems later on, you'll see this and why they both make sense. But that's what we're going to talk about with rates and instantaneous rates of change.